All right, so let's ask the question, how long does it take for the thermal wave to be felt at some position? So once you have this disturbance occurring, how long does it take for delta t to reach some position x? So let's develop an approximate model that's going to help us with this. The approximate model is, it is not exact, right? It is not like a formal derivation. It's just this conceptual model that we can use to estimate things about the behavior, just like we do with the BO number and just like we do generally with resistances. We can just estimate something and get some useful information out of it. So this approximate model, let's use this resistance idea and apply it here. So what I'm going to do is let's take this part of the domain that's been affected by thermal wave growth and make a control volume out of that. Right, so I'm going to draw a box around the part of the domain that's been affected. This distance here is delta t, that's the thermal wave depth. We're forcing some q dot to come in on this side. And we're going to call this dotted line that I drew our control volume. So I guess some things to point out here. Effectively, what's happening inside this control volume is there's a change in internal energy with time. Right? You're starting to grow in temperature on average, and so that corresponds to some du dt that occurs actually inside this domain. So we actually have to account for that. Let's go through and do a control volume analysis on this control volume that I drew, and you'll kind of see where this is going. Again, the goal is we're trying to develop a model for how long it takes delta t to reach some position. So the energy balance here is what's coming in. Well, we have q dot coming in. We have leaving. What do we have leaving? Well, if you look, there's actually nothing leaving right down here. The temperature gradient is going to be 0. So there's nothing leaving this domain. By definition, the way I drew the domain was to include everything that's been affected. So the thermal wave has not yet reached just past the edge of what I drew. Therefore, nothing can be leaving. So there's nothing leaving. So if something coming in is q dot. Leaving is 0. There's no generation, but there is a stored term. So let's subtract off the stored term du dt equals 0. Now we need rate equations for these. We have, for the rate equation for conduction, instead of using Fourier's law, I want to do this as an approximate model. So let's use a resistance model as our rate equation. So let's say this is now Ts minus T initial. See, we have up here Ts. Down here we have T initial. That's the driving temperature difference over the resistance. So let's call this resistance for the plane wall. And we'll come back to this, right? The du dt term, du dt is going to be equal to the mass times the specific heat times the change in temperature with time. So this is, for us, mass is, specific heat is C. Mass is going to be rho times the volume times dt. So a few things here. First, let's come back to the things that we don't actually know. We know Ts minus T initial. We don't know our plane wall. So our plane wall here is, for plane wall resistance, is thickness over KAC. So what's the thickness that we have to deal with? Well, that's actually delta T, right? The depth of this thermal wave. So delta T over K times AC. What else don't we know? So volume here is going to be AC times delta T. And then we can take this up here. And then, since we don't have like an exact model for temperature, let's just go through and do an approximation. Again, we're doing this as an approximate model. So let's say dt is actually, well, what's the approximate average change in temperature for this control volume, right? Going from T initial to Ts. Here it's going to be Ts minus T initial over 2. Hopefully that makes sense, right? If you look over here, you have the close, approximation is like average being this straight line, average of that straight line. So that's like a reasonable approximation. Okay, and then we now can go through and plug all this stuff into our energy balance and then see what that ends up with. So let's see, we have our Q dot term, that's K times AC times Ts minus T initial over delta T. That's approximately equal to ddt of, let's see, Ts minus T initial over 2 times rho C delta T AC. So this simplifies down to the following, which is 2K over rho C, over rho C. It's approximately equal to delta T times d delta T dt. And hopefully you can see where that came from. So let's simplify this in one way, and let's introduce this idea of thermal diffusivity. So thermal diffusivity is called alpha. So this is thermal diffusivity. Alpha. Alpha is defined as K over rho times C. And it has units of meters squared per second. So with this definition of alpha, we can just rewrite the equation, taking this K over rho C and putting it on one side. So we use alpha for this term right here. This gives us 2 alpha is approximately equal to delta T, d delta T dt. So let's bring the dt here. This is a separable ODE, right, first of all. So we've just developed a differential equation in terms of delta T, which is good because we're trying to find some relationship that involves delta T. So we can bring the dt over to the left-hand side and then separate things out. So let's do that. This becomes 2 alpha dt is approximately equal to delta T d delta T. So I can integrate both of these sides, right? I can integrate the left-hand side with respect to dt, and I can integrate the right-hand side with respect to d delta T. And when I do that, I get, I'm running out of room here, but I get 2 alpha T is approximately equal to delta squared T over 2. Let's see, solve this for delta T. So I want to solve this for delta T. And that gives me, let's keep this as approximate. Delta T is approximately equal to 2 times the square root of alpha times time. So this result here is an important result, right? This tells us the thermal wave depth, this delta T, as a function of time. So if you know something about the properties of the wall, if you know something about the amount of time that's elapsed, you can predict the thermal wave depth. So one kind of interesting thing to note here, right? When we were back up here, when we were back up in this equation here, we had on both sides of the equation Ts minus T initial. We could pull that out because Ts is constant, right? We're holding that constant. T initial is a constant. You can pull that out and cancel it out. So it turns out that the rate, the thermal depth, right, the depth of that thermal wave does not depend on temperature, which is really surprising, right? You think like the amount of time that's going to elapse if I really ramped up that temperature on the wall, that it would shorten the amount of time that it takes for the thermal wave to reach the center. That's not the case, right? It's purely the depth is purely a function of properties of the material, like conductivity, density, and specific heat. Now, like if you're heating something up in the stove or oven or something, the size of that thermal wave depends on temperature, but the amount of time that it takes to reach the center does not depend on temperature. So it's kind of an interesting observation. Now we have a model that's this relationship between time and the thermal wave depth. Let's reconsider this model a little bit just to kind of change it around. And let's think about if we want to estimate the amount of time that it takes for the thermal wave to reach some depth L. Right? So we're trying to estimate now time for a particular depth. So to do that, we just say, all right, we want L to be equal to 2 square root of alpha times time. And then we just solve for the amount of time, right? Just straightforward algebra here. So T is equal to L squared over 4 times alpha. The reason why I'm doing this is this particular group, right, this here, is a time constant. We can call this actually tau diff, right? Tau diff has units of seconds. It's the amount of time that it takes for the thermal wave to penetrate into the depth L. So this is a really useful metric that we can use to kind of characterize the system along with this tau LC. So where tau LC is how long does it take to respond to the surroundings, tau diff is basically how long does it take the thermal wave to penetrate into some depth that I care about. In other terms, or another way of thinking about this is how long does it take for thermal equilibrium to be achieved in the internal part of the conducting body. So let's now just take a minute to compare these two, and hopefully it'll become clearer what I mean by tau LC and tau diff. So tau LC, right? Tau LC is a response to the temperature response to the surroundings. This is like the bulk response of the entire body. The formula for this is the surroundings resistance times the capacitance of the object, mass times specific heat. The response is to a forcing function where the time constant is basically 1 times tau LC, right? So what I'm saying here is if you have a forcing function, the time response to that occurs in 1 times tau LC. Whereas for the diffusive time constant, it's basically 1/5 of that. Another way of saying the same thing is that the time to equilibrium is 5 times tau LC. The time to internal temperature equilibrium is 1 times tau diff here. Right, so this is just a way of comparing. If you compute both of these two time constants, you end up with a good description of both how long it's going to take for the entire body to sort of fully respond to the surroundings temperature change. That's tau LC. And you'll have some understanding of how long it takes internally for a uniform temperature profile to start to develop, and that's tau diff.